Right, that seems to be working. Great. Welcome back to my Game Engine stream, where we make the Blaze engine together. I'm just keeping it on stream because that's a habit. Everything is documented on stream, more or less. However, today we would not be implementing completely new features, but instead just finishing up all the remaining features of the things that we did not take care of during the previous streams. And we'll start off by actually trying to render Sponza. Sponza is a very well-known scene on online, like for graphics, because it was originally used by CryEngine to demonstrate global illumination. It's the Sponza Palace. It's an actual place that is represented as a 3D model. And for those who know like graphics, you probably have seen this quite often, right? So this is the Sponza. So I already have Sponza downloaded. I should be able to simply go to Blaze, go to the top and say Sponza, right? It's actually Sponza inside Sponza. So instead of a GLB, we have a GLTF file. So not everything is within that file. That will cause bugs to start off with. So let's start. And there we go. Did I crash because it cannot load anything? So we'll look into that. So what is happening here is we just take CGLTF. We ask CGLTF to get us all data. And from a buffer data, we get the image. In this particular case, the buffer does not contain any data, right? All images are separately available in the folders. So we need to actually grab them separately. So instead of using base color image buffer image, what I will be using is base color image URI. Okay. So what is URI? It just checks if there is a universal resource identifier that is available. So normally this is null when the data is already loaded, but this will be non-null if the data is not loaded. So if, and there's an else, of course, and there's this whole loading here, and this particular part can be swapped out into something that goes in here, because that way we don't have to bother with different allocation and deallocations. So we just let, if it's from memory, STB image can load from memory. That's what we're doing right now. But otherwise, if we have a file, we'll just get STB image to load from file. All right. So how do we do that? Here we can open a file, or we can directly just call STBI load here, in which case I need to get this point of data down there. Okay. Options. Design can change over time as required. But this entire thing out here is load image, right? Just this part is load image. So it's not a big deal for me to say that this is technically a part of load image. So I just put it here, load image. We can always make it a function later on if we need it to be a function. So that's it. That's one type of load image. This is from memory. Yeah, that should be fine. From memory. Then the other one is based on if base color image has a URI. So this is an else, effectively. And here I will assert that the buffer view exists before I even start anything. Okay, so base image URI, we simply have to load. So do all of this from the URI. We can directly pass it. It will not be correct, but we'll get to that in a second. So STB, STB, I load. There we go. It asks for a file name, which is nothing but the base colored image, URI. It asks for an end pointer. That's going to ask for the other details that we had over there. So we fix it like this, and we're done. Now texture data should be loaded if the URI is correct. There's a little catch here. So if you actually run it, we'll find that the URI is relative to the GLTF file, while what we're trying to do is not relative to GLTF file, right? We're trying to load it from wherever we are, which means we need the path of the GLTF file, which we can get from where we load the model. So here's the load model, right? You get the file name, it has the path. It simply takes the file name here, doesn't do anything with it. Let's swap that to stdfs. I think I need to first include the file system standard library. So that's include file system. There we go. To come down there. Sorry. Load model. Okay. So we take the file name stdfs. Oh, it's file system, right? And you can say get fs path directory. So we need to first create a path out of the string, which is file name. And then we can get a directory out of it. So directory. And that will give us the directory of this particular thing. So that is model directory. So I can say auto model directory equals that. So that assigns a path here. If I'm correct, path actually allocates memory internally. It's just based on some sort of set. Okay. But path internally does contain a wide string right there. Okay. So because of this, we have the directory of the model. And now we just need to pass this in for everything we do. Well, not everything. We only need this to go to the materials, which are somewhere in there, let's say. So model directory, we put down here. We do process node, take all of that, take this entity model thing here. And in the same thing, I will add the directory somewhere. So I believe this should be a good place. So pass in model directory. Process node here takes std, file system, path, takes that as a reference, model directory. Okay. And in here, again, it just calls other process nodes. Model directory goes in there. Process mesh, which also requires this model directory. Then in process mesh, we add that. So, std file system directory. So it's path model directory. Okay. One more thing. This is const. right? We're not actually going to modify it anyway. Should not be doing it. So we should put it as const if we're not expecting to modify it. Model directory. All right, that seems fine then. So now that mesh has model directory, material needs to get it. As you can see, it's just model directory being passed all the way down. So we go to material, std, file system, path, const, and model directory. Okay. And finally, now that we're here, we can just add model directory to the URI wherever it is that we need it. Okay. So we have the model directory here. We're doing stdi load here. So here I would say model directory dot relative path look. So it should take a parameter normally. Okay. Need to check what's root directory in this then. I think I might have made a mistake. That's the wrong one. cd fs file system root directory. Oh, root directory will give us slash. That's not what we want. Yeah, this should be parent path. All right, that's more appropriate. And here we take the parent path. So that's model directory dot and check append. Oh, I don't like that at all. That is oof. We'll use it as it is for now. Don't really have much of an option there. But that doesn't mean I like it. Still doesn't work because CSTR becomes the wrong type. So back we go. This instead is to as look generic string dot CSTR. Now it will work. We'll see if it loads or not first. Okay, so far so good. That's it. It has loaded. You can see it's spinning, which is not precisely what we would like, but it's working. So that's Sponza. What we will also do is we will go inside the Sponza model and sit somewhere close to the center. So we do that by first changing, we'll leave that as is. We go to, I think this is loaded. The camera position is set in this data. So this is all over the place and we will be cleaning this today. As time passes, anybody who's worked on this will stop remembering where everything is. And unless everything is designed properly, that you remember where it is or like can find it out very fast, these kind of mistakes are going to happen where you just don't remember where it is. So it's best to fix it when you can. Z equals -1. That's done. Target is at 0, 0, 0. I can always say target is at x equals 2, but and y equals 1. That way I can put z equals 0. So this will be inside the model now. We can start again. Okay, the model's going to rotate, which is not exactly what we want, because that's going to be a bit disorienting. So let's remove the rotation code for now. Yeah, it's right here. Control C. And we start. Yeah, it load. Oh, hey. I did not get time for it. I've been quite busy. Sorry, I have not. So today I'm not looking at the chat the whole time. So yeah, this is it. You can see it's like colored very weirdly. There are certain things which are a bit wrong, and we'll fix that. My voice has changed a bit, yes. Um, it's temporary. So anyway, that's Sponza. It has loaded. It is working. I don't like how we've loaded it. That's not very clean. So we'll have to fix that. There's also a few more things, like the lights right now are set up in a place that we can't see them anymore because they're massive. So instead, I will change the light range to 5 and move them all within the Sponza model. So x equals 2, y equals 2, z equals 2. Actually, y for all of them should be 1. It should be -2 here instead. That way they're just at the end of the corridors. And I'll switch the colors to white. Just so we can see if the colors are even correct or not. Sorry, the light shape is correct or not. All right, start. So you can see on the right-hand side in the diagnostics, the process memory keeps changing. And there it is. We have one light, which we can see. The others are not visible. We would like to move around. And that was one issue. So the light was a bit below. We would like to move around a bit with the camera. That is something we should set up at some point, moving cameras. Loading. There we go. And the light doesn't seem to be very well set, does it? So I'm going to remove this one too. Just keep one of them at -2, 1, but that's where we're facing. Let's see if that does the job. Still behind us. The light seems to be behind us right now. 2, 1 is where we're facing then. Now the light should be ahead of us. Okay. Does appear to be ahead. However, it's far too close for us to see much of a difference. And it seems the attenuation is not set up properly. So yeah. As you can see, attenuation is per light distance as opposed to light distance squared. Actually, with gamma correction, this should not be a thing. But oh well. We'll see how that goes. Okay. Okay. Let's push it down all the way to the end of the corridor. I think that's at 5. Unsure if it is at 5. Yeah, okay. So you can see it has been pushed down to the end of the corridor. Now, a few things you can notice is the grass or the foliage on the sides is a bit off. we don't support alphas, which means any transparent material actually just uses the whole polygon that they're using. And second, the lighting looks very flat on the ground. That's because we're not using normal maps. Neither of these are currently supported in the system. So let's actually add them. First, we go to the model loader. Instead of CPP, we go to the H file first. Because we just take a texture in the material. Material, yeah. So in material, we just say a single texture and that's it. So here, instead of saying texture, I will say albedo, which means the, color. Not exactly, but kind of. It generally means the amount of light that is being proportionate amount of light that will be reflected out of this when any light goes in. Normal will be the second one. Third one would be metallic roughness occlusion normally. So metal rough. I won't put occlusion right now. And last one is emissive. Okay. Normal text, metal rough text, emissive text. As you can see, there's already metallic roughness and everything. Those are default terms. Similarly, base color, and we also need an emission factor, so emissive. Okay. Or I can make it emission text. All right, so that's our new material. Given this, normal text may or may not exist. It's not guaranteed for any part of the system. But if it exists, we should be able to use it. Now let's do a bit of counting. So anything that goes to the GPU should ideally have this kind of a counter. So 4, normal text again takes 4, which is a total of 8. Metal rough text is another 4, which is total of 12. Then emission text is another 4, which is total of 16. Okay. Then padding, which takes 0.4, which is another 4, which was 20. Then roughness, which is another 4, 24. Barrel. Then metallic, which is 28. Base color, which is not 0.4 anymore, that is actually 16. So 28 plus 16 becomes 44. This one will be another 16, which rounds it up to 60. Okay. So this is the current setup. This is 60 bytes. And we should be able to use this. However, there will be a small problem with padding because 16 is supposed to be aligned by 16 on the GPU, not for push constants. But later on, we will put this into buffers, so then we can have an issue. So now I can see this is actually flocked. Offset is still the same, but GPU data size is 60. What's wrong with that, huh? Okay. So why is that? Is there a padding somewhere we're not looking at? Now it's 64. So it went from 64 to 72. That single padding actually consumed a lot more space than we expected. Okay. So 04 is 2024 plus 16 is 40, and this one will be 56. Again, not a good rounded number, but something we can actually start working with. That checks out. So this is fine. Okay. Moving on, we copy this material definition. I'm not taking the albedo here because it's not that important right now. And that is the same we will have on this side. So let's see. Yeah. So now what do we have? So we have sampler 2D dot RID met normal ID. Then there's metal rough ID. Then there's emission ID. We don't have emission here, so it wouldn't matter right now. Oh, there's a little problem there. Roughness and metallic are reversed. Oh well, fixed now. Base color is a float 4 and another float 4 for emission. Cool. So that should be fine. Should be is a keyword. Generally, we will have to test the offsets being correct or not. Now, another thing is we're not actually sampling normal or anything, which we should. However, normal mapping is a little more difficult than whatever we've done so far. Mostly because normal mapping requires inverts of a part of the matrices. So what happens is when we scale our matrix, right? Scale anything, the normal scales are now with it if we try to apply the basic transformations to the normal. This would be fine if the scale is uniform because a normal is just directional. So XYZ scales and normal remains the same because it will, normalize itself to the right value. However, if you scale non-uniformly, which means x-axis is half, y-axis is still full, then the normal will actually no longer be a normal. So instead of using just the matrix of transformations that does the world transformation for us, what we really need is a matrix that only does rotations and a matrix that corrects for, the scaling problems. And that's just like based on the inverse matrix. You can see it in here. So if you go to model loading, it's in lighting, I think. There's that. So they have it in here about scaling and everything. Scaling, also right here. Yeah, here. So if you scale by a weird value, your normals are also going to be weird. So you need to use this inverse transpose matrix. You can do this on the GPU. It will be expensive because each vertex shader will try to do this. What we will do is we'll just do this in the fragment shader. Okay? So my bad. It'll be expensive because we're doing it in vertex shader. What we'll do instead is we'll do this on the CPU. So we'll get this C++ program to be like C++ part to compute it and then just send the results to the GPU. So we only do this once per model, right? That is kind of expensive even now. And this is something we can later on optimize by removing what we call non-uniform scaling. So non-uniform scaling is more or less the issue we're trying to fix here. So if the scaling was uniform for some of the models, we don't need to compute the inverse at all, because there we can just, use an identity matrix and get done with it. Anyway, right now I will just add it in. Just need to find where we have the transform. Should be in the PCB and there. Normal correction, or actually I'm just going to pass inverse transform and we can do the rest on the GPU. So we get the inverse transform from here. Now on the CPU side, we need to get this. Maybe not call it a inverse transform at all. So normal correction. Yeah, okay. Normal correction sounds more appropriate. So we know exactly what it is. And on the CPU, we can do the normal correction each time. So when we get to the world transform, we do this whole thing. That's our world transform. Now we need, so DirectX, XL in matrix inverse. So it takes a determinant and a matrix. Why does it need a determinant? Let's search this one. It's an optional out. Okay. All right. We will say it's null pointer and we'll pass in the matrix. So that gives us the corrected matrix, which is DirectX. That's a matrix. Normal correction. It's not actually the normal correction because we still need to do DirectX transpose. So let's say transpose. And then we need to do DirectX. I need to remove the translation from this whole thing. So translation is all the end bits, let's say. So what I'll do is I'll just say normal correction. So we have all the rows. I think the last row gets the terms. I don't like it when I have to deal with row or column majors. So I'll just hack through this. Beta is not a part of material. I will add the rest too. So material dot normal texture, metal rough texture, and emission texture. Okay. Cannot convert this because it takes a base color texture. It expects nothing, and nothing. And that should be fine now. Start. Okay, that built. Yeah, ranges are not proper anymore. We'll get to that in a second. Okay, so we have this normal correction. Let's look at the data. 1, 1, 1. So of course we can't see anything with this. This thing has a value. Not bad. There. No translation. This is just a scale. So we continue. Scale again. To an error. Push constant buffer must be contained. Size is 192. Yes, data. Push. Second range. 56 here, XML matrix. It actually needs a second one. So times 2. Okay. And that actually sets the push constant range correctly. When we go into the data here, and inside place, when we get the material, we copy all of that. Size of world transform plus size of in. It's a normal correction. There we go. Okay, start. Okay. Normal correction gives us response identity. Okay, let's see this one. Yep. That's scale as well. Identity. Scale. Alright, that's not being very helpful to us. So what should we do? I can just use one from here. So look at world transform based on that issue. Okay. Got normal correction again. We have the word transform here. We can look at word transform. Let's skip that. So okay. Now let's see what's the normal correction is. Still identity. It's still identity. Okay, I'm going to close that for now. So with normal correction done on this side, let's just do the thing on GPU itself. We have float 4x4. Normals have to be corrected. So inside vertex main, here, after the normal has been multiplied by the transform, it will also need to multiply it by correction, I think. I'm using multiple. Should stop using multiple browsers all at once. Okay. Whenever you apply non-uniform scale, yes. So that's it. Normal corrected. So normal has to be transformed here. So this instead would be normal correction. And we don't actually need to do anything. We've already set this to 0, which means translations will not work on the normal correction anyway. Okay. With that, we can continue moving on. Normal correction from here can move down to where we actually use it. So we use it here. Compute the normal correction. And then for draw indexed, we simply have to, so before draw index, we simply have to push it. primary push parcels. So we miss and layout. Fixed stages, size of word transform. It takes size of normal correction, and the data is normal correction. Great. So that should be able to do its own job. Dot it, run. There are some issues there. We will have to fix it. So it has this buffer block with range 192, which is outside the push constant range of 184. You can see the colors look a little off, right? They look a little green, and there's a good reason for it. If you open render doc, it's going to be the alignment I talked about. At least I think it's the alignment that I talked about. What's this? So you can see how much work that loading is doing. And you can see how render doc actually renders. So how we are actually rendering it. There's nothing, then we render one thing at a time. So one by one, everything gets rendered. Okay. Mesh viewer, actually pipeline state, background shader, go. That's the one. All right. So what's happening here? So we're expecting an emission ID, material ID, texture ID in the right places, and we're getting them in the right places, okay? However, base color, as you can see, the byte offset. So everything's offset by 128. So let's forget 128. So this is 128. So 0, 4, 8, 12, 16, 20. This is not 24. It's down all the way to 160, right? The difference between metallic and base color is a lot. It's 12, right? So this is 12 byte difference. And the reason is this has to be aligned to 16 byte boundaries. Base colors are expected to align to 16 byte boundaries, while 148, like the thing after 148 is not a 16 byte boundary. There's multiple ways of solving this problem. I'm going to solve it with something simpler and more, let's say, modern Vulkan, which is ask the alignment of the GPU to be similar to the CPU. So we go to the render device. Not the render device, we go to, yeah, it is the render device, CPP. We go to the features, and one of them has a scalar layout. Yeah, there we go. So that's what we need. Now for device address will be after. Okay, looks good to me. Build it. Run it. Is it still green? It probably is. Okay. And file. We will also fix it in here. So instead of doing anything else, we will just move this to the top. That way, these are already at the 16 byte boundary. And then these can just fit in however they like. All right. Scalar block layout is set up. This should normally lead to scalar values. I think it's because in compiler steps, I have not set scalar block layout. So line scalar block scalar layout. command line compilation, scalar. Yeah, it's here. So force GLSL scalar layout. Then we need to actually send this properties, custom build tool, build. Okay, there we have. So here, I'll just go in and I'll write that force GLSL scale layout. Okay, build solution. We build solution because it's just the mesh. Started. Some issue at submit. Okay. What issue at submit could exist? We have the Vulkan config on already. So scalar block layout is also set up. The issue that we're facing at submit is because we changed the alignment in here. So we changed the directions up here. We also have to change them in model loader. So here, these two need to move to the top. Now this is 0, 16, 0, 16. And then these become, this is 0, 0, 16. How can it be 0, 0 anywhere? 16, 16, sorry. Then that takes 0, 4 plus 16, which is nothing but 20. 24. It's 0, 4, 28. 0, 4, 32. 0, 4. 36 and 0, 4, 40. That seems wrong to me. Just 16, 16. It's just to be 32 right there. Plus 16. So that's 36 on here, 40, 44, 38, 52, and 56. Okay, that checks out. Resolution. No overloaded function because the order has changed, so this order also has to change. Base color texture. To move this before that. So now it takes base color, emission, then all the other textures. Build that. Start. No longer green, I hope. There, no longer green. Cool. So now we have the normal textures in memory. Sorry, we don't have them in memory. We simply have normal textures supported. We need to actually load them. So model loader, CPP, we have our textures. Where are they? So this is the base color texture. Loads the whole thing from here. And one of the small issues with this, let's say, is right there. So we, have to manually rewrite this every single time for the entire process to work, when it doesn't necessarily have to, go through this entire process every single time. So fetch image, that's here. Do the create info, that's fine. So we take the sampler creation out of this. because every material will require a sampler creation irrespectively. Just create it anyway. So if it exists, we're good. If it doesn't exist, we don't do anything with it. Push back the sampler in here anyway. No failures in the middle. That is a failure here. So that requires us to actually retry the sampler. Okay. So this is fine. Can leave it in for now. Is color image. So CGLTF image. Then we do the stuff here. We need to do the same stuff for normals and for normal image and everything else. So what I will do is I will capture this entire block. Say refactor, extract method. So that becomes load image, load texture actually. Okay, and you can see it takes a lot of things as inputs. What is value 1? Y is a value 1. It's the return value from outside the statement. All right, that seems to be fine. We need to check that. Is that okay? Sampler, where do we need sampler in here anyway? I'll just do the extraction and then we can look at it. So load texture. Texture. Okay. Start. Build solution. Okay, that's fine. Now, here's what's happening. So texture image is a texture ID here that's being returned. That's being accepted and assigned to. But in reality, we can just return it, right? So out here, we create the texture. If it fails, we assign UNT max there, value 1, so that we can return true. What we are trying to return in other cases is the material index. So we don't actually need the value 1 here. Instead, we just load the texture. So that means either we load a texture or it fails. So we can return malloc for that instead of doing that whole set a value and return thing. Now that that's done, it should be able to set values for us automatically. It shouldn't take as an input the texture ID because that's what it's returning. So here I will actually have an auto texture ID. There we go. And at the end of this entire thing, it's being loaded, the return false gets converted to return base color texture, right? Now we can go to the definition, change the name to texture. And we can go to this and change this to image or CGLTF image. All right. Now what's happening? So this should load everything for us. This is where we come. We don't have the value one. It's no longer required. So if load texture will actually auto base color texture equals load texture. We do the optional there. So now if there is, okay, hold on. We need to remove this one. So what we're saying here is if there is a base color texture that is returned from this, and it's not a false optional. If it's a true optional, then we have a value, and base color texture is nothing but base color texture opt dot value being moved. So std move. Cool. So that's base color texture for us. Done. Else, well, it's rather simple. We first do a delete. So render device, and we have a delete. So we can destroy sampler. So we destroy that sampler, which is from there. So sampler create info. No, not create info. It's just called sampler. Hold on a second. That's if we push material back. Otherwise, there was an error, or we did not have a material to push in. Okay, yes, this is fine. So we destroy the sampler. We need the device. This is the first parameter. Sampler is the second parameter. Allocation callbacks are the third parameter, and that's it. Destroy it, and we return int 32 max. That's the end of base color texture. We do another because we need to load normals. So that's a normal texture up. That's a normal image. This whole thing goes outside this if. Come back to it in a sec. So put there. Remove this. Actually, yeah, we will rename it again. So here it's just material.normal texture, right? Normal texture, which is a texture view that does exist. What do we check here? We check base color texture.texture. So that's what we'll check here as well. So now if there is a normal texture, then there's a normal image. This again changes to normal texture image. Base color texture opt becomes normal image. Normal texture opt base color texture becomes normal texture, which doesn't exist. So we go to the base color texture and just change. So we add a few more things. So normal texture. We add metal rough texture. We add emission texture. Okay, so these are the textures. So normal texture is set here. All fine. We use it down here. So emission goes after normal texture. So that's normal texture. Metal rough text is metal rough texture. Emission text is emission texture. Move. And move. Okay. What is the second set of brackets out here? Okay, it must have its own good reasons for it. Let's actually start naming these. So sampler equals sampler base color actor equals this thing. In fact, I will remove it and redo it. So dot designate initialization. So sampler is sampler. Base color is base color factor. Emission is empty for now. Albedo texture is base color texture. Normal texture is dot move normal texture. Metal rough is metal rough texture. Move. Emission texture is emission texture. Move. The roughness is roughness texture. So roughness is just roughness. Metallic is just metallic. And we're good to go. There we go. So now all of these are set. We need to just load them here. Are these fine for now? Yes, they look so. Render device, texture manager, destroy, free texture, and we have to free the previous one, which is base color texture. There we go. Alright, let's remove. Okay. Normal texture, we do it again. Because we have metal rough. So that one is actually inside PBR metallic roughness. So we go back to the PBR metallic roughness version. So metallic roughness dot PB. Sorry. Metallic roughness texture. There we go. Dot texture. Does it have a texture? We put this entire thing here. Replace that thing right there. Normal image becomes metal rough image. Normal texture opt becomes metal rough opt. Metal rough opt gets assigned to metal rough texture, and we're done. Normal texture should be deleted if we fail here. Finally, there's emission. Again, emission, I think, is in the same vein as normal texture, so we'll put it there. So this is emission. Yeah, it does exist. Emissive texture. Emissive texture. Emission image. Oops. Which one was it? Normal texture. We leave normal texture alone. This is emission texture. There we go. This one becomes emission texture opt. Okay. So with that, we can continue moving on. So that loads emission texture, everything else should be loaded. We need the emission factor here. So base color factor. We'll also load the emission. So emission factor. So emission factor, which is emissive factor. Sorry. Zero material dot emissive factor dot 1 material dot emissive factor 2 material dot emissive factor emissive strength. What's emissive strength? It's just a single float. It says emissive strength. Wow. There we go. So we pass emissive strength in. You can check what it's for. So GLTF, emissive strength. Okay, so what is emissive strength for? So it's an extension. Emissive factor and emissive texture to control the light emitted in the range of 0 to 1. In HDR, you might need more than that. So emissive strength being 5 means you multiply the base factor by 5. Yeah, there it is. So you can see it's actually doing sRGB in linear here. However, we use the sRGB factor as a part of the format. So when we load, any image load will automatically be linearized. So emissive strength is something we need to pick out. So we just pass it as the last floating point, and we can multiply this relatively easily. Okay. Rebuild solution. I haven't set it here, so emission factor. There we go. Done it. Now it's taking a lot of memory, eh? It has to load every normal map and everything else we have. That's 2.4 gigs of loaded memory. Interesting. All right. So we're not using normal maps yet, so nothing changes in the way, like in what we see. We need to start using normal maps. So we go in here. That's lighting. We do have normals inside lighting. This is a world normal. It only tells us where the overall surface is pointing. What it doesn't tell us is where our current location is, where our current pixel is pointing and where its normal is. So how do we change this? How do we get the remaining parts? So other than normal, we also need to pass what is known as a tangent vector and or a bitangent vector. So all of these needs to now arrive to the GPU. So again, go back in there, inside model loader, look at the vertex data that we have. So that's vertex as a normal right there. We now need another thing called tangents. Yay. This is called a tangent. Okay. Normal set to 111 is wrong. I mean, it will be overwritten, but it should just be z equals 1. And tangent space. So GLTF default tangent. So yeah, tangent is a vec4. XYZ is normalized and W is handedness of the tangent basis. Okay. So this can't be float 3, it has to be a float 4. I will put it there and I will say the tangent is along X for now. For effective packing, I'll move it down here. Okay. Tangent. We'll just use it as it is for now. So we go to the model loader CPP. Position. There we go. So you have position, normal, export, color. We'll take color. This color uses rect 4. It may use rect 4. So you take that into account. But for now, we're fine. tangent attribute name. This is always vec4. Here it's not color attribute, instead it's tangent attribute. There we go. We don't care about the equals 3 side, and this isn't a problem either. That was unexpected. All right, so that's the else. I'll remove the else, nothing happens. I remove the bracket here, I remove the bracket there, and there we go. Okay. So that's the tangent attribute. It's going to load. XM float for colors becomes nothing but tangents. So tangents. Tangent attribute is fine. All of that is fine. The density size if required. Tangent there and tangent here. There we go. So tangents have also been set. So on this side, we will have a tangent available to us. So we can say 4 tangent and it is available. On pipeline creation side, we need to provide it to the vertex input. So there we go. Color, tangent, location 5 is color, location 4 is tangent. Format is still the same. Binding is fine. Build and run. Yeah. Succeeded, start. I don't know why I'm running it. It's more or less a habit. Just to see if things are working fine or not. Okay. So now that we have both the normal and the tangent, we can do a little thing, which is we can start creating a matrix known as a TBN matrix. This has to be constructed on the fragment because normal vectors will get interpolated as they pass from one side to the other side, which means all of their directions will be different on each pixel. Similarly, the tangents will also get interpolated. So, and that's also going to be interpolated. So we take the tangents onto the other side. And we will then normalize all of this before using. So here we say tangent. Okay. So what's the whole thing here? So first we say let n equals normalize normal. Okay. So we first normalize normal. Let t equals normalize tangent. We normalize both of these. Now, the basis of these will actually have shifted a little bit. They will not necessarily be correct. So we're not going to just let this be and we'll have to correct them. Normal is considered correct. So we'll have to work based on that. Now we're working on a right-handed system. So normal when crossed with tangent should give us bitangent. Can always check that. Bitangent from normal. Yeah, why not? Stack exchange. Let's go. So yeah, bitangent is cross of normal with tangents. Although, so let B equals cross of normal with tangent. Now, another key thing that will occur is normal and tangent are not necessarily perpendicular because of the linear interpolation. Okay, so normal is a float force, tangent is a float force. Neither of these are valid for cross products. Cross products are already defined in dimension 3 and dimension 7. So that gives us a B as a cross product. This will have to be normalized because, as I said, tangent and normal are no longer orthogonal, so they will have a little bit of an issue. And now that this has been done, so we have a normal that faces up, we have a tangent that faces along the surface, which gives us a bitangent with faces perpendicular to both of these. That's guaranteed right now. So it's perpendicular to the normal and to the bitangent, and to the tangent. And since we know tangent is the arbitrary version while normal is the ground truth, we construct normal by saying cross of bitangent with normal. So then we say T equals normalize cross. Actually, we don't need to normalize anymore because B is normalized and N is normalized. And they're both perpendicular guaranteed. So what's wrong with that? Oh, there we go. So I'll just go to close that editor and open it again. Syntax highlighting looked very off-putting. Okay. So that should create our tangent properly. Now we create a float 3x3 PBN, which is created from the 3x3 from the tangent, bitangent, and normal. That's the TBN matrix. When did you start the stream? I think 1 hour ago. So this is TBN. Now what we need to do is for every point, we will pick out the normal from the normal texture. So we will let the N exist. The remaining we'll only do if we want to fetch the, let's say, corrected normal, right? So what I will do now is I'll move this out and I'll say sample get normal. Let's just get normal for that particular point using the normal, the tangent, and it should be able to find everything else. It will need UV, so take UV0. So now it has normal, tangent, and UV0. I think that's all it needs. So we can say now vec float 3 get normal. It takes as input a normal, float 3 normal, float 3 tangent, and float 2 UV0. So first it normalizes normal into N. Does the T be to get TBN matrix? Now if let normal text equals PCB dot normal ID, normal text has to be sampled, so we say normal text dot sample. We sample it from, hold on, location, which is UV0. We need an offset, we don't have any, so we can just sample from UV0 and call it a day. GB. Okay. And this has to be multiplied with the TBN matrix. So 1 TBN, comma, this thing, And that's the one we have to return. All of this is actually inside here because we don't want to put all that effort in doing all of this if there is no normal texture attached. So in the event there is no normal texture attached, that's the else case, we don't actually need else. Return, and we simply return the normalized normal here. We return just the n. So what I can do is I can move this out and just return that. It was computed anyway, so we can just move it out there. Okay, now what? So get normal will get us our data here. Something wrong? Yeah, so XYZ, XYZ, done. The solution, that looks okay. Get normal looks fine. There is a point that uses normal here. So halfway vector, which uses light direction plus view direction. That doesn't matter to us. Normalize of a normal XYZ, right? So that does use M there. And halfway vector, view direction. That's actually wrong. It's not halfway vector with view direction, it's halfway vector with normal. Okay, weird solution. Start. Of course, because we've been only modifying the shader. Start. Yeah, something's wrong. Vertex attribute location 4 is not consumed by vertex shader. Okay, so the TBN matrix is wrong because we actually never pass the tangent because we never assign it in here. So after we get all of that data, so output tangent equals null PCB dot normal correction note 4, and here we take a tangent. So that's tangent, which comes in as an input. We don't actually need to do anything else with it. Start it. Of course. Start. Let's see what this turns out to be. Probably a horrible mess of corruption. Well, yes. It is a horrible mess. Corruption, I can't say. Let's output just n. So this n that we got there. Let's output that as a result. So we can say return float 4 n comma 1.0, right? So normal can be in any direction. What we want is we want to be able to see it visually irrespective of the direction. So we will say multiply, no, we'll say divide by divide by 2. So multiply by 0.5 plus 0.5. So it can go from -1 to 1. That's what it used to be. And now we've swapped to this thing. Well, I've only done it on stream, so you can just sum up the number of hours of the stream. I don't know exactly how long it has been, but that's how long I've spent on this so far. It's not a game particularly. I'm making more of a system to render and everything. So that's the normals that we're visualizing. The normals on the floor are mostly facing up. As you can see, there are some intricate details on the normals on the left side, on the curtains. So that is nice. You can even see the normals in the stonework, but some of the normals just fall apart when you look at the walls and everything. They are effectively reversed. So how do I fix this? When in doubt, go to learnopengl.com. So we can see what the TBN matrix construction is supposed to be like. I may have been using the wrong TBN matrix. Entirely possible. So there's the tangent space. They're manually calculating it. We're not. So T tangent, B by tangent, N this thing, more back thing for TBN. That is more or less exactly what we're trying to do here. But they do multiply the model projects here. Okay. The TBN matrix seems to be constructed in the vertex shade of something. That's interesting. Okay. I can't particularly figure right now what has gone wrong here, but we can figure that out as we go. So yeah, I learned. Normalized tangent before XYZ. That's not good. Better. I think I'm gonna cheat a little bit. Yeah, that's not the one. No. This is an old engine that I was working on long time ago. But the thing is, it still has the stuff I need. So what I can do is I can just look at how I did it back then and figure it out. So this is not it. Okay, search for TBL. There we go. So by tangent was a negative normalization of this. And tangent was constructed from differential equations instead of using the tangent given to us automatically. That's interesting. Hold on. The basis function gives us the tangent. Tangent normal times TBN normalized gives us the answer. So here after mul, I need to normalize this. Normalize. And another thing is, this is fine. The tangent actually flips directions depending on the W value. So multiplied by this is tangent dot W. Okay. Build solution. And we start calling it first rebuild. Okay, and start. Unless zero doesn't have tangents at all, that could be a problem. That could be a real thing. Again, now you can see the surfaces seem to have roughly figured themselves out. Still look wrong to me. Still look incredibly wrong to me. But we can figure it out. Yeah. That's no good. That's not good at all. Oh, yeah. This should be negative normalization there. I'll just look at it again. So normal tangent like this, by tangent like that, TBL constructed, and then passed in. What I can rather easily do is literally the exact same thing out there that we saw me doing in the previous one, which is calculate tangent on the fly in the fragment shader. Okay. So this is what we're trying to do. You see the values are all over the place there. Wish viewer, you can see if the tangents exist. So those are minus ones, and the tangents do exist, and they are valid tangents. Okay, so it does provide us valid tangents out here. Well then, does this have valid tangents? It does. No. Hold on. So if B is negative of loss of MD, so L is normal, goes up. D is tangent, goes in a direction, gives you B, which is other side is negative. So now if I try to do B cross N, my T fails. So this also has to be negative if I want to use it like that. No, that didn't work. DVL also needs to be transposed. Start. Okay. There we go. So the issue isn't fixed yet. As you can see at the end, there are two sides which are flipped in terms of their color, but we're getting close. So one of the things I forgot was I'm using slang now instead of GLSL. So GLSL uses column, uses, no, actually that will make a difference. The constructor to float 3 by 3 is row by row. So we need to change it to column by column. Okay. Sure, if I need to do that, it'll be exactly the negative tangents. I do need to actually do that, but we'll see. Just for fun. Yep, so you can see the problem inside is fixed, but now there's a problem in front of us. Very interesting. A lot of things I need to fix. I think from this time onwards, I will be doing most of these things offline. I don't think I'll be streaming anymore. Mostly because I will be doing a lot more of this. And I don't think I have the energy to stream that many hours of it. Like 1 hour of stream, 2 hours of stream is doable. 4 hours is too much. And when I really work on this, like during vacations, it's 8 hours and so on. So at that time, I'll just work offline. So goodbye. And looking forward to having you back to see the videos I make about it. See you guys. Have a good time and goodbye.